Welcome back to the Deep Dive. Today we're plunging into a topic that silently powers so much of our digital lives. How computers sort and predict not just what's next, but what kind of thing it is. Imagine your bank deciding on a loan, or your email catching spam, or even a hospital triaging patients, all without being able to correctly categorize. Thankfully, we have the elegant power of classification models. We've gathered some fantastic source material on predictive analytics, ranging from, foundational concepts to advanced evaluation techniques. Our mission today is to cut through the noise, giving you a crystal clear understanding of what a classification problem entails, the diverse models designed to solve it, and critically, how we measure their real-world impact.
Indeed. And we'll start by defining the core challenge of classification, then move into specific models like logistic regression, discriminant analysis, and the surprisingly effective naive Bayes.
Okay.
We'll also explore the broader unifying framework of generalized linear models and wrap up with the essential tools for truly assessing if these models are, well, doing their job well.
So if you've ever wondered about the intelligence behind your spam filter or the algorithms making high-stakes decisions, you're about to get a fascinating peek behind the curtain. Okay, let's unpack this. To kick us off, what defines a classification problem in the landscape of predictive analytics? How does it differ from, say, predicting a specific number?
Well, at its heart, classification is about categorization. Instead of predicting a continuous numerical value, like a house price or maybe a stock's future value,
Right.
we're predicting which predefined group or class an observation belongs to. Think of X as your set of input features, perhaps a customer's age, income, and past spending habits.
Yeah.
And Y is the specific category we're trying to predict, such as, will they default on this loan, or is this email spam?
So we're talking about qualitative outcomes.
Yeah.
Yes or no for a loan, spam, or ham for an email.
Exactly.
Or even stroke, drug overdose, or epileptic seizure for a patient. These aren't numbers, they're distinct labels.
Exactly right. The goal is to build a function that takes your input data X and predicts its category Y. But what's truly powerful here, and this is key, is that we're often not just interested in the final label. We want to know the probability that X belongs to each category.
Oh, okay. So it's not just this insurance claim is fraudulent, but this claim has an 80% chance of being fraudulent. That probabilistic confidence is, wow, a massive leap forward.
It really is.
But what happens if we try to force something like a simple linear regression model onto this kind of categorical problem? Does that even work?
That's a great question, and it highlights why specialized tools are necessary. I mean, you could try. If you code your categories as zeros and ones, say 0 for no default and 1 for yes default, and run a linear regression, you'll immediately hit a logical wall. Your predictions could easily fall below 0 or shoot above 1, which, makes no sense for a probability.
Right. A negative probability of default is meaningless, or more than 100%, also meaningless.
Precisely. And it gets worse. If you have more than 2 categories, take your emergency room example. 1 for stroke, 2 for drug overdose, 3 for epileptic seizure.
Yeah.
Linear regression would impose an arbitrary numerical ordering on those. It would suggest the difference between stroke and drug overdose is somehow the same as between drug overdose and seizure.
Which is totally misleading.
Completely. It just doesn't reflect the underlying reality of the conditions. This is where we need models specifically designed for qualitative responses.
Okay, so if linear regression isn't the right fit for handling probabilities, what's the go-to approach that gracefully stays within those 0-1 bounds?
This is where logistic regression truly shines. Its mathematical structure, it's built to ensure that our estimated probabilities, Px, always fall between 0 and 1.
Okay.
The formula, Px equals E0 plus 0, 1x, 1 plus E0 plus E1x, it might look a bit intimidating at first glance.
A little bit, yeah.
But its brilliance is that it's essentially an S-shaped curve, right? A sigmoid curve. No matter what linear combination of r plus 1x you feed into it, the output, Px, always neatly falls between 0 and 1. It gracefully translates our linear evidence into a proper probability.
So it's about transforming a linear relationship into a probability. Oh, and I understand there's a neat trick with log odds that makes it more interpretable.
Exactly. If you rearrange that formula, you get something very elegant. log px O(n) plus a1x.
Ah.
This transformation, called the log odds or logit function, it creates a linear relationship that's much easier to work with mathematically. It essentially takes the odds of an event happening versus not happening, then logarithmically transforms it, giving us a linear equation connecting our predictors to those odds.
This next part is where the true power, I think, comes into focus. How do these models actually learn those Voronix's values, those coefficients that define the S-curve? Do they just guess until it looks right?
No, not at all. They use a sophisticated but actually quite intuitive method called maximum likelihood estimation, or MLE.
MLE.
The core idea is to find the parameter values, the betas, that make the observed data most likely to have occurred.
Can you give us an example? Make that concrete.
Sure. Imagine you flip a coin 10 times and you get, say, 7 heads. MLE would tell you that the most probable biases of that coin, the P, or probability of heads, is 0.7.
Okay, that makes sense.
It's the P that maximizes the likelihood of observing your specific sequence of 7 heads and 3 tails. The model applies this principle by calculating a likelihood function for your entire data set and then finding the coefficients that maximize that function.
That makes intuitive sense. So what does this all mean when we apply it to a real-world problem, like, say, predicting credit card default?
Right. Our sources highlight a powerful insight from the credit card default example. If a customer has a balance of, let's say, $1,000, their estimated probability of default might be really low, maybe 0.006.
Very low.
But if that balance jumps to $2,000, the probability skyrockets to 0.586.
Wow.
This isn't just a number change, it's a critical insight. Logistic regression reveals that risk isn't linear. A relatively small increase in balance can trigger an exponential jump in default probability.
That quantifies risk in a way simple linear models just can't. Vital for banks, I imagine.
Absolutely vital.
It's quite a jump. It really shows the nonlinear nature of risk.
Yeah.
And what about when we add another predictor, like whether the person is a student? Our sources reveal a kind of curious effect here.
Yes, confounding variables. This is where multiple logistic regression provides critical clarity. When we just look at students versus non-students in isolation, maybe students appear to have a higher default rate.
Okay.
But if we include balance in the model alongside student status, the student coefficient actually becomes negative.
Wait, hold on. So students actually default less than non-students if we account for their balance.
Yeah.
That's a surprising reversal.
Precisely. It suggests that students, on average, tend to carry higher balances, right? Which leads to a higher marginal default rate when you look at them overall.
Oh.
But for any given balance level, a student is actually less likely to default than a non-student. Multiple logistic regression can tease out these subtle confounding relationships that, simple one-factor analyses would completely miss. It offers a much more nuanced understanding.
We've focused on classifying into 2 categories so far. Binary stuff. But what if, like our emergency room example, we have many more than 2 possible outcomes? Stroke, overdose, seizure.
Yeah, good question. That's where multinomial logistic regression steps in. It's a natural extension for when K, the number of classes, is greater than 2. It leverages a clever function known as the softmax function.
Softmax sounds interesting. What's its role here?
Small ass. In a way, it is. Think of logits as the model's raw evidence scores for each class before they've been converted into a proper probability. They can be positive or negative, large or small.
Right, just raw scores.
Softmax then takes these scores and cleverly transforms them into probabilities that are both positive and, crucially, sum to 1 across all categories.
So for our emergency room patient, if the raw scores were, say, 2.5 for stroke, 1.0 for drug overdose, and 0.5 for epileptic seizure, how does softmax turn that into usable probabilities?
Well, it exponentiates each score, so e to the power of 2.5, e to the 1.0, e to the 0.5. Then it sums those exponentiated scores up.
Okay.
And finally, it divides each individual exponentiated score by that total sum. For those specific scores, it would calculate probabilities of approximately 0.737 for stroke, 0.164 for drug overdose, and 0.099 for epileptic seizure.
And those add up to 1.
Exactly. It ensures a consistent probabilistic interpretation while correctly normalizing across all the classes.
That gives a clear, interpretable output for multi-class problems.
Got it. Now, the sources also introduce a fundamentally different way of thinking about classification. Discriminative versus generative models. What's the core difference in their philosophy?
Yeah, this is a really important distinction. If we connect this to the bigger picture, logistic regression is Discriminative.
Discriminative, meaning it directly models the conditional probability of y given x. That's PRY, YKX, XX. It essentially learns to draw boundaries between the classes.
Okay, finds the dividing line.
Exactly. Generative models, on the other hand, take a different, more sort of holistic route. They model how the data X is distributed within each class and the overall likelihood of each class itself, PRY.
And then they essentially flip that around using, it sounds like Bayes' theorem again, to get the probability of a class given the features we observe.
Precisely. They use Bayes' theorem to derive the posterior probabilities, PRY, KXX. Bayes' theorem, in its essence, provides a systematic way to update our beliefs, our probability estimates, as new evidence becomes available.
Right.
It describes the probability of event A happening, given that event B is true, based on prior knowledge about A and B. It's a really powerful framework for inferring class probabilities from feature distributions.
So discriminant analysis is a prime example of leveraging that generative approach and Bayes' theorem. When would a data scientist reach for, say, linear discriminant analysis, LTA, or quadratic discriminant analysis, QDA, instead of logistic regression? Are there specific situations?
Yeah, there are. A key insight surfaces when we consider certain data characteristics. For instance, when classes are very well separated, like really distinct groups. Logistic regression's parameter estimates can sometimes become unstable. LDA doesn't suffer from this issue. It's also often preferred when you have more than 2 response classes, and interestingly, when you have smaller data sets.
Smaller data sets, why is that?
Because LDA makes stronger assumptions about the data, specifically about the distribution of X within each class, assuming it's Gaussian. These assumptions mean it needs lift data to get a stable estimate.
Okay, so what's the fundamental difference between linear discriminant analysis, LDA, and quadratic discriminant analysis, QDA, in practice? They sound related.
They are very related. The crucial distinction lies in how they view the shape or spread of the data for each class. LDA assumes that the variability of the data represented by its covariance matrix is the same across all classes.
Same shape for all clouds of points.
Kind of, yeah. This leads to linear decision boundaries, like straight lines or flat planes separating the classes. QDA, however, relaxes that assumption. It allows each class to have its own unique covariance matrix.
So different shapes are allowed.
Exactly. This results in more flexible, curved, or quadratic decision boundaries.
So if the underlying cloud of data points for different classes has roughly the same shape and orientation, LDA is a good, simpler fit. But if those shapes are distinctly different, QDA might be better for drawing those more complex, curved boundaries.
That's a great analogy. The choice often comes down to the classic bias-variance trade-off. LDA has fewer parameters to estimate, making it less prone to overfitting, especially with smaller datasets. But it might have higher bias if the equal covariance assumption isn't true. QDA, with more parameters, is more flexible and can capture more complex boundaries, lower bias. But it needs more data to avoid high variance and overfitting.
Makes sense. And once we've built these models, LDA or QDA or logistic regression, how do we actually know if they're any good at classifying? Our sources use a confusion matrix for that credit data example. Tell us about that.
The confusion matrix is absolutely vital. It's the starting point for really understanding model performance. For that LDA model on credit data, it gives us a clear breakdown in a table.
Okay.
You have true positives, correctly predicting default, true negatives, correctly predicting no default, false positives, predicting default when there was none type I error, and false negatives, predicting no default when there was a default type 2 error.
Got it. So a true negative means we predicted no default for someone who truly didn't default, save them some hassle. And a true positive means we correctly flagged someone who did default. The bank wants that.
Correct. But what's often most crucial is analyzing the errors. In the credit data example, the LDA model made, I think it was 23 false negative errors.
Okay, missed 23 defaults.
And 252 false positive errors. Predicted default, but they didn't.
Okay. So quite a few more false positives.
Yes. This resulted in an overall misclassification rate of 2.75%.
2.75% error. That sounds pretty good.
Is it? Well, it seems low, but then the sources mention something called a null rate of 3.33%. Why is that important context? The null rate is your essential baseline. It's the error rate you'd get if you just took the lazy approach. Classify everything to the most frequent class. In this credit example, no default was the vast majority. So if you just always predicted no default, you'd only be wrong 3.33% of the time. That's the actual default rate.
So our model's 2.75% error rate is better than just guessing the majority, but maybe not dramatically better.
Exactly. Your model must significantly beat that null rate to prove it has actual predictive value and isn't just reflecting the imbalance in the data.
And we can also strategically prioritize different types of errors by adjusting our prediction threshold, can't we? It's not just about overall error.
Absolutely. This highlights the real-world implications. You might set the threshold differently depending on the cost of each error type. For medical diagnosis, a false negative, missing a disease, is often far worse than a false positive, telling someone they might have it when they don't.
Right. You'd rather investigate a few healthy people than miss someone who's sick.
Precisely. So you'd lower the threshold, accepting more false positives to minimize false negatives. For spam detection, maybe you prioritize reducing false positives. You really don't want important emails ending up in the spam folder.
Even if a bit more actual spam gets through.
Right. The threshold lets you tune that trade-off based on the specific application's needs.
Okay, shifting gears slightly to a different approach mentioned in the sources. Naive Bayes. Now, that name implies something.
Yeah.
Well, simple, maybe even a bit unsophisticated.
Slight chuckle. It does. And the naive part comes directly from its core, simplifying assumption that all features are conditionally independent of each other given the class.
Conditionally independent. What does that mean in practice? Like for spam detection?
It means if you know an email is spam, that's the given class, the probability of it containing the word Viagra is considered completely independent of the probability it contains the word prize or free.
That sounds, well, pretty unrealistic in many cases, right? Those words probably do appear together more often in spam. So why is naive Bayes so widely used and often surprisingly effective?
That's a great question, and it's one of those fascinating paradoxes in machine learning. While the independence assumption is often technically violated in reality, naive Bayes simplifies the computations immensely. This is especially true when you have a very large number of features, like thousands of possible words in text classification.
Okay, so it scales well.
Incredibly well. Multivariate methods like QDA or even LDA can really struggle with high dimensions because they have to estimate complex correlations between features. Naive Bayes just looks at each feature separately given the class.
Kind of a divide and conquer strategy.
Exactly. And despite its strong, often wrong assumption, it frequently produces surprisingly good classification results. This is often attributed to the fact that requiring exact independence isn't always necessary for good classification, and the simplification reduces the model's variance, making it more robust, especially with limited data.
So it can handle things like, say, qualitative features, like email provider, Gmail, Outlook, alongside quantitative features like number of links, without getting bogged down by their complex interdependencies.
Yes, it's remarkably versatile for these mixed feature vectors. You can model the quantitative features with something like a Gaussian distribution, maybe, and the qualitative features with simple proportions or frequencies within each class. The model calculates the likelihoods for each feature independently and then just combines them using the prior probabilities of the classes in Bayes' theorem to arrive at the final posterior probability for each class. It's computationally very efficient.
Our journey's taken us through classifying binary outcomes, multiple outcomes, generative versus discriminative models. Now, as we've explored these diverse models, you might start to wonder, is there some kind of grand unifying theory behind them all?
That's a great way to think about it.
And our sources reveal a fascinating framework that connects many of these seemingly disparate approaches, the generalized linear models, or GLMs. What's the big idea here?
Generalized linear models provide a really elegant, unified framework. They extend the concept of ordinary linear regression to handle a much broader class of response variables, not just continuous ones, but binary, qualitative counts, and others too.
So we know linear regression handles continuous numbers. Logistic regression handles binary outcomes. What other kinds of data can GLMs expertly manage?
Well, a great example is Poisson regression. It's excellent for modeling count data. Count data, like
the number of hourly users checking out bikes in a bike share program, or maybe the number of calls arriving at a call center per minute, things you count.
Okay.
Linear regression would be a poor fit here, right?
Yeah.
It could predict negative numbers of bikers, which is obviously impossible.
Right? You can't have negative bikers. That really highlights the practical issue.
Exactly. Poisson regression ensures automatic positivity for counts. It does this by modeling the logarithm of the mean number of bikers, or calls, or whatever count, as a linear function of the predictors.
Ah, so it transforms the mean first.
Precisely. And that's the core genius of GLMs, the link function. This function transforms the mean of the response variable so that it can be modeled linearly.
Okay.
For standard linear regression, the link function is just the identity. The mean itself is linear. For logistic regression, the link is the logit or log odds function. For Poisson regression, it's the natural logarithm. So the real genius of GLMs is that they show us linear. Doesn't just mean straight lines in the original data. It means there's a predictable, systematic structure, but maybe within a transformed version of the mean response.
You've got it. It allows us to use the well-understood machinery of linear models for a huge variety of data types, ensuring our predictions are both accurate and sensible, respecting the inherent nature of the data. Probabilities stay between 0 and 1, counts stay positive, and so on. It offers incredible flexibility.
Building these sophisticated models is one thing, but how do we truly know if they're earning their keep? This leads us to a crucial step: rigorously evaluating their performance. Our sources introduce a fundamental tool for this, that confusion matrix we talked about earlier.
Right. The confusion matrix is the foundational tool. Can't really evaluate a classifier without it. It breaks down predictions into those 4 critical categories: true positives, TP, true negatives, TN, false positives, FP, and false negatives, FN.
And from this simple 2x2 matrix, we derive a whole suite of metrics that tell different stories about how well our model is doing. Right. Accuracy, sensitivity, specificity, precision, and something called the F1 score.
Indeed, and each offers a unique perspective, crucial for different situations. Accuracy. That's the overall proportion of correct predictions, TP plus TN, total. Good for a general sense, maybe for balanced classes like predicting tomorrow's weather. But it can be really misleading if one class is rare.
Right, like the default example. High accuracy might just mean you predicted no default every time.
Exactly. Sensitivity, or recall, that's TP plus FN. It measures the model's ability to find all the actual positive cases. How many of the real defaults did we find? Crucial in medical screening or fraud detection, where missing a positive case is costly. You want low false negatives.
Okay, finds the needles in the haystack.
Good way to put it. Specificity. That's TN plus FP. It's the model's ability to correctly identify the actual negative cases. How many of the non-defaulters did we correctly identify? Essential, where a false positive has serious consequences like wrongly accusing someone, low false positives.
Got it. Doesn't cry wolf too often.
Right. Precision. That's TP plus FP. Of all the times we predicted positive, how many were actually positive? Very important for things like spam detection. If an email is flagged as spam, predicted positive, precision tells you how likely it really is spam. High precision means few legitimate emails end up in the spam folder.
Okay, minimizes those annoying false alarms.
Yes. And finally, F1 score. This provides a balanced measure. It's the harmonic mean of precision and recall to precision plus recall. It's useful when you care about both finding the positives, recall, and being right when you predict positive precision, like in many medical diagnoses.
So lots of different ways to slice the performance. But this next part is where the true strategic decisions often come into play. Beyond these individual metrics, our sources introduce the ROC curve and AUC. What are they and why are they so powerful for evaluating classification models?
Okay, the ROC curve, that stands for Receiver Operating Characteristic, is a brilliant graphical representation. It plots the true positive rate, sensitivity, on the y-axis against the false positive rate, which is 1 specificity, on the x-axis.
Okay.
Across every single possible prediction threshold. Remember how we said you can change the threshold?
Yeah, to trade off false positives and false negatives.
The ROC curve shows you that entire trade-off visually. Each point on the curve represents a different threshold.
Ah, so it's not just one snapshot of performance at one threshold, but a comprehensive view of how the model behaves across all levels of certainty for what constitutes a positive prediction.
Exactly. A model that bows up towards the top left corner is better, because that means you can get high sensitivity, finding positives, with a low false positive rate. A diagonal line from bottom left to top right represents random guessing.
Okay, you wanted to hug that top left corner.
You do. And the AUC area under the curve then summarizes that entire ROC curve into a single, highly interpretable number.
Just one number for the whole curve.
Yep. An AUC of 1 signifies near-perfect predictive capability. The model can perfectly distinguish between the classes. An AUC of 0.5 means the model is no better than random guessing. the diagonal line.
Wow.
So the AUC gives you a great overall picture of a model's discriminatory power, independent of any specific threshold choice. It's fantastic for comparing different models or understanding performance when balancing those different types of errors is critical.
Wow, okay. We've covered a tremendous amount of ground today.
Yeah.
Seriously. From the fundamental act of categorizing an email to the sophisticated math behind predicting credit default or triaging patients in an ER. We've seen how logistic regression deftly handles probabilities, how generative models like LDA and QDA offer robustness under specific conditions, and even how naive Bayes can be surprisingly effective despite its, well, naive independence assumption.
And we wrapped it up with the essential tools for actually evaluating these models. The versatile confusion matrix and all its derived metrics, and then the powerful, all-encompassing ROC curve and AUC.
I think a key insight from all of this is that each model offers a different lens, right? A different way to view your data and make predictions, each with its own strengths, weaknesses, and assumptions.
So what does this all mean for you listening in, whether you're analyzing data for work, maybe building these models yourself, or just navigating an increasingly data-driven world? Understanding these classification techniques gives you, I think, a profound advantage.
Absolutely.
It's not just about getting a prediction, but understanding why a model made its decision, what assumptions went into it, and the inherent trade-offs involved in its design and evaluation. That's the critical part.
So for your final provocative thought, consider how these classification models, with their different assumptions and evaluation metrics, sensitivity, specificity, precision, force us to think deeply about what kind of error we're most willing to tolerate in different real-world scenarios. Is it missing a sick patient? Flagging a good email spam? Denying a loan to someone who would have paid it back? And what do those choices truly say about our priorities in an increasingly algorithm-driven world?